Hello guys, let's continue. Last time we stopped at this point. We were doing the Cauchy's convergence criterion. We have proven it one way, and now we are proving it the other way. So the second half of the proof. Let our sequence be fundamental. Then we have this line. Fixing m, this number, we can see that for any n, basically xn is in an epsilon divided by 3 neighborhood of xm. Since only a finite number of terms of our sequence have indices not larger than mn, we have shown that our sequence is bounded. That's where we have stopped last time. Now let's continue. Now let's for any n, we can set an equals an infimum of xn where k is greater or equal than n, and bn equals supremum. So this is infimum and supremum of all of the terms after some specific number. So from this definition, we have then for any n, an less than an plus 1, less than bn plus 1, or less than bn. From the way we constructed those numbers. Then we have basically a sequence of nested intervals. There is a point common for all intervals in Bn. There is a common point. Let's call this point A. So for any n natural, we have that an less than A less than Bn. Then for any k greater than some specific number n, we have an, which is an infimum of xk, k greater than n, should be less or equal than xk, less or equal than supremum of xk, less or equal than, not less or equal, strictly equal bn. Okay, very well. Very well. Now, from the last two lines, we can see that number a is inside this interval, and also number xk is inside this interval. So less than b n and greater than a n. This means, hence, the distance between those two numbers, a minus xk, absolute value, should be less than bn minus an. So basically, those two numbers both lay on the same interval, so the distance between them is not greater than the length of this interval. Okay, very well. Now, we know this statement, this part. Hence, xm minus epsilon less than infimum of xk less than actually equals an, which is less than bn, that is supremum of xk, which is less than xm plus epsilon. Epsilon divided by 3, not just epsilon divided by 3. Okay, so this distance, bn minus an, this difference, is less than difference between those two numbers. Hence, a minus xk less than bn minus an less than 2/3 epsilon. Less or equal here, which is strictly less than epsilon. Strictly less than epsilon. So, for any epsilon greater than 0, we have constructed a number n, that number from the previous, from the beginning of the proof, such that for any number k. Look, it says that we said that n is greater than n, small n greater than capital N. And then we said over here that k is any number greater or equal than small n. This basically means any number greater than capital N. For any k greater than capital N, it follows that a minus xk less than epsilon. So this means that there exists a limit of our sequence, and this limit equals a. End of proof. Any questions? Guys, masks.
Why have we used modulus in B and minus?
It wasn't necessary. Yes, we could have skipped it. Yes. Маска. Да, она работает лучше так, да. Okay, any more questions? Moving on. Definition. A sequence xn is called increasing if for any natural n, xn is less than the next one, xn plus 1. And similarly, we have is decreasing if for any n xn is greater than xn plus 1, xn is, what do I call it? Non-increasing. So strictly and not strictly increasing or decreasing sequences. Sequences of any of those types are called monotonic sequences. Monotonic. I remind you a definition of a bounded sequence. Well, actually, I will need bounded above sequence. This is nothing new for you. This is just a definition of a bounded above set. But I will remind you anyway. Definition: a sequence Xn is bounded above if there exists, what does it call it? M, real number M, such that for any n, Xn is less or equal than capital N. Bounded above sequence. Theorem, Weierstrass. I think I have spelled this correctly. In order for non-decreasing sequence to converge, it is necessary and sufficient that it be bounded above. So, a non-decreasing sequence converges if and only if it is bounded above. Let's prove it. Necessity is obvious. Since any convergent sequence is bounded. So if a sequence converges, then it is necessarily bounded, and in particular it is bounded above. So this part is obvious. Sufficiency. The set of values of our sequence is bounded above Hence, there exists a supremum of all of those numbers, which I will call S. This is a real number. So, since our set is bounded above, it has a unique supremum, as we remember, that is a finite number. Okay, this number S. Let's write down definition of supremum. Actually, not exactly the definition, but from this definition of supremum. From the definition of supremum, we have for any epsilon greater than 0, there exists a number, an element of our set that is greater. I will say it. I will write it down first. From our set, such that xn is greater than s minus epsilon. So this is the first part of the definition of supremum. If you remember, it says that for any number smaller than the supremum, there exists an element of our set that is greater than that number. So number s minus epsilon is a number smaller than s. So there should be an element of our set that is greater than this number. Okay, good enough. Good enough. Since xn is non-decreasing, we can say that for any n greater than capital N, look, here that element in the previous line I called x with the index capital N. So basically I have found a number of that index, of that element. And since our sequence is non-decreasing, any elements after that element should be greater or maybe equal. It follows that I will write like that: s minus epsilon is smaller than x capital N, which is smaller or equal than x small n, which is less or equal than s. This last bit is because s is an upper bound of our sequence. And then let me write down that s is smaller than s plus epsilon. Epsilon is a positive number, so this is true. Well, basically that's it. Hence, for any epsilon greater than 0, I have constructed a number n, natural number, such that for any n greater than n, basically this says that xn is smaller than this number and greater than this number, which means that xn is inside epsilon neighborhood of S. xn is inside epsilon neighborhood of S. Well, which means there exists a limit of xn equals S. So I have shown that any non-decreasing sequence that is bounded above converges, and its limit is its exact upper bound. Okay, very well. And you of course understand that we can formulate and similarly prove a theorem about a non-increasing sequence that is bounded below. Okay, good enough, good enough. Now we have this sequence, Euler's number, definition. A limit of 1 plus 1 over n power n equals e, n tends to infinity. So I will not prove it right now, but you can read the proof of the next statement in our book on page 65. I checked page 65. We need to prove that this sequence 1 plus 1 over n power n is convergent, and to prove it we basically use the Weierstrass theorem by proving that this sequence is bounded above and increasing. Hence, it is a convergent sequence, and hence, well, let's call this limit of this sequence number e, which is approximately 271. Okay, let's take a break. Okay, our next topic is subsequences. Partial limits. Definition. If xn is a numerical sequence, and nk is an increasing sequence of natural numbers. I will write it down once again. This is the same statement. So this is a sequence of natural numbers. So for any k is nk is also a natural number, and also it is an increasing sequence. So any next term of our sequence is greater than the previous one, and also nk is less than nk plus 1. Then the sequence yk, which is constructed as xnk. So for any number k, we take nk and use it as a number of the term of the sequence xn. Then this sequence is called a subsequence of xn. So basically we are taking the terms of our sequence in the, maybe not all of them, but infinitely many of them, in the correct order. This is the idea. Okay, theorem. Balzana-Weierstraße. Any bounded sequence has a convergent subsequence. Any bounded sequence has a convergent subsequence. Let's look at the proof. So let our sequence xn be a bounded sequence. Well, what is a bounded sequence? It means it has an upper bound and a lower bound. Basically means then there exist number a1 and number b1 such that for any n it follows that a1 less or equal than xn less or equal than b1, which is the same as to say that xn lays inside a closed interval a1 b1. So all of the terms of my sequence lay in this closed interval. So this is just from being bounded. Let's construct a point C1, which is A1 plus B1 divided by 2. On the interval A1, B1 lay infinitely many terms of my sequence, all of the terms of my sequence. Let's look at the intervals from A1 to C and from C1 to B1. So this is basically this picture. A1, B1, and this middle point C. C1, let's call it C1. Let's look at the right and left halves of this interval. At least one of those halves contains infinitely many terms of my sequence. Because otherwise, if both of those halves contain only finite amount of terms, then the whole interval would contain a finite amount, which is not the case. Okay. So since sequence xn has infinitely many terms on an interval A1, B1, it has infinitely many terms on что такое? At least one of the intervals from A1 to C1 or C1 to B1. So infinitely many terms of my sequence lay at least in one of the halves. It could be the case that both halves have infinitely many terms. Yeah, this could happen. But at least one of them definitely have. Yes. Let A2, B2 be that interval. So A2, B2 is A1, C1 if it contains infinitely many terms of xn and C1, B1 otherwise. So if the left half contains infinitely many terms, I take that half, otherwise I take that half. Okay. And then I'm going to repeat this step again and again. Repeating this process. On a step number k, we will have a closed interval AKBK containing infinitely many terms of my sequence. I will once again cut it in half. Let CK be AK plus BK divided by 2. At least one of the halves contains infinitely many terms of my sequence. Let AK plus 1 BK plus 1 be AK CK if it contains infinitely many terms of xn and ck bk otherwise. So after this step number k, I have constructed an interval ak plus 1 bk plus 1, which also contains infinitely many terms. And I repeat this process. Let me write it down. And also let me note that those intervals AK, BK are nested intervals. Can you see? Then let me, how do I write it? Let me write it here. Thus we have constructed a sequence of closed intervals должно быть K или M? Yes, K. K, BK. Each of them containing infinitely terms of xn. Okay. Nested sequence, each contains infinitely many terms. Very well. Now, let's construct a subsequence. Let n1 equal 1. Then we can see that y1, which is equal x and 1, which is equal to just x1, lays inside the first interval a1, b1. This is obvious because just all of the terms of my sequence lay inside this interval. Can you see? Yeah, so this is obvious. Now, interval a2, b2 contains infinitely many terms of xn. Hence, there exists a number n2 which is greater than n1, such that y2 equals x n2 lays inside this interval a2, b2. So there are finitely many terms of my sequence which has indices less than n1. Actually there isn't any, but still it's finitely many. Hence, there is at least one term of my sequence that wrong explanation. This interval contains infinitely many terms of my sequence, and only finitely many of them could have an index less than some specific number. So there is at least one, actually infinitely many of them, that lay on this interval that has indices greater than that specific number. For example, this one. Okay, and then as you can imagine, I'm going to repeat this process. Repeating this process. On step k, I say that there exists a number n k plus 1 which is greater than nk, such that yn plus 1, which is yk plus 1, xnk plus 1, lays on the interval a k plus 1, b k plus 1. So basically I have constructed a subsequence such that each of the elements of this subsequence lays on the corresponding closed interval from this sequence of closed intervals. Okay. Let me write it down. This way we have constructed an increasing sequence of natural numbers and k thus yk is a subsequence of xn. Okay, good enough. So we have constructed a subsequence, and now I'm going to prove that this subsequence is convergent. Let's get back to our nested sequence of closed intervals. A nested sequence of closed intervals A, K, B, K has a common point. Let's call it A. Yes, A. A, real number. Now, when I have constructed those intervals, on each step I divided the previous interval in half. So the length cuts in half on each step. So the length of the interval number k, that is bk minus ak, is exactly b1 minus a1 divided by 2 power k minus 1. And this sequence tends to 0. Since the length of those intervals tends to 0, for any epsilon greater than 0, there exists capital N such that for any k greater than capital N, bk minus ak less than epsilon. Since for any k a k less than a less than bk, and bk minus ak less than epsilon, we have a is less than bk less than ak plus epsilon, from which would follow ak less than a plus epsilon. Let's check it once again. So a less than bk because of this, because a is a point that lays inside this interval. And bk is less than ak plus epsilon because of this line, of this part. And from here it follows that ak is less than let me think about it. The other way around. The other way around. AK is greater than A minus epsilon. From this inequality, I'm taking this and that. From here, it follows that way. Okay, very well. Similarly, A is greater or equal than AK, which is strictly greater than bk minus epsilon. From here, it would follow that bk is less than a plus epsilon. In the same way, that and that. Okay. Very well, very well. Now, since AK is greater than this number and BK is less than this number, this means that an interval AK BK lays inside an open interval A minus epsilon, A plus epsilon. By definition, because the left side of this interval is greater than the left side of this interval, and the right side of this interval is less than the right side of this interval. Yes, so this is correct. And of course, this interval is the epsilon neighborhood of A. Very well, very well. Now, since the terms of my constructed subsequence yk, let me put it. Since for any k yk lays inside this interval AK, BK, which lays inside this interval, it follows that it follows that for any k greater than n, yk lays inside epsilon neighborhood of A. Yes. So this part is true for any k at all, any natural number. Then, since for any k greater than capital N, we have this part, then yk is also inside this neighborhood of A. So, for any epsilon greater than 0, there exists capital N such that for any k greater than capital N, yk lays inside epsilon neighborhood of A. That is, there exists a limit of yk, and this limit equals A, real number. Hence, sequence xn has a convergent subsequence yn, yk. End of proof. So this way we have constructed a convergent subsequence. Any questions?
In that line, I said that there exists n2 greater than n1. It's n2.
N2, yes, N2.
It's any number. So what is it saying? Is it any number greater than n1, or is it?
There exists such a number. Well, actually, on this first step, it's not a very interesting statement because any term of this any number, natural number, would be greater than n1, well, except then just 1. But I'm building up for the general step. So if we have constructed, if we have any specific number, natural number nk, since we have infinitely many terms over here, then there is a term from this interval with the index greater than that specific number. Let's call this index nk plus 1, and let's call this element, this term of the sequence, yk plus 1. I will not make a test out of it, but just for yourself, think, why do I have to specify that on each step this part is important? Why couldn't I just take any term from this interval. I could have constructed any term of this from this interval, and I will have a sequence of terms of my original sequence. And then this part, this last part would totally work, and then thus I will have a sequence of terms of my original sequence that is convergent. Why is it not good enough? Think about it yourself. I have a couple more minutes. I can start the next topic. Let's move on, unless there are any questions for this topic. Let's move on. Next topic is limit of a function. Definition. A set u delta. So this is like a neighborhood of a point, but with a dot on top of it. So this set is just a neighborhood of my point, except the central point itself. This is an interval x0 minus delta to x0, and from x0 to x0 plus delta. So this is a neighborhood of x0 except the x0 itself. So this set is called a deleted neighborhood. Deleted epsilon neighborhood. Deleted delta. Neighborhood of x0. So, a deleted neighborhood of x0. Definition. A deleted neighborhood, delta neighborhood of infinity, I will define as just neighborhood of infinity. Let's start with plus infinity. So deleted neighborhood of plus infinity is the same as neighborhood of plus infinity, and this is a set from delta to plus infinity. A deleted neighborhood of minus infinity is the same as neighborhood of minus infinity. This is from minus infinity to minus delta. And a deleted neighborhood of infinity without sign is neighborhood of infinity without sign. And this is just a union of the previous two sets. From minus infinity to minus delta, and from delta to plus infinity. Okay, those definitions we will use next time, and I don't have any more time for the next step. So, any questions?